Welcome everyone to this presentation on self-triggered control for near-maximal average intersample time. I'm Gabriel Gleizer. This is a joint work with my colleague Khushraj Madnani and my supervisor Manuel Mazo at TU Delft. If we're talking about self-triggered control, we need to talk about event-triggered control, a relative called ETC, which is a simple and hold control mechanism where the state of the plant is only sent to the controller when some state-dependent condition happens. Self-triggered control, or STC, is a close relative in which the controller decides when to request the next sample, typically by predicting when an associated ETC condition would happen. Their objective is to reduce communications for control when compared to traditional periodic sampling, enabling larger networks of interconnected control devices and reducing energy consumption of battery-powered modes used in wireless control. However, are these strategies optimal in reducing such communications? If you look at how ETC is designed, it becomes apparent that it's not the case, because ETC is a greedy approach to optimal sampling. In ETC, this condition that dictates the sampling is typically a surrogate of a Lyapunov condition. So samples are being checked until some underlying Lyapunov condition is violated. And as soon as it's violated, the next sample is sent. Now, notice that any previous sampling time could also be chosen because it would also be satisfying this Lyapunov condition. And by sampling at this last moment, you could enter a portion of the state space where the deadlines are very short and you have to sample very often. So could it be that if we have a strategy that knows how to look ahead in the right way, we can sample earlier, but reap benefits in the long term, because then we could stay in the portion of the state space where we need less frequent samples. So this is our problem statement. We treat the triggering condition from ETC as a deadline that guarantees some control performance, but can we design a sampling strategy that samples no later than ETC would, but gives a higher average intersample time? In particular, we aim at a higher or optimal smallest average intersample time, or SAST, which is the infimum amongst all points in the state space of the limit average of the observed intersample time run that starts from this initial condition. So this is Ki of x is the ith intersample time observed from the closed loop system starting with initial condition size 0 equal to x. Our approach to find this strategy is using weighted finite state abstractions. So we have the concrete system, which is infinite state. And for every point in the state space, we have a deadline given by the PETC, which in this case would be 3. And so we will have choices of sampling at 1 or 2 or 3. And each choice would lead us to different points in the state space. This is an infinite problem. And we can abstract to a finite state system with weights. So this would be our abstraction, where we have now finitely many states, each of them labeled by their deadlines. And we can, again, choose actions 1, 2, or 3. And the abstraction can have transitions being non-deterministic, meaning if I choose 3 here, I can either end up here again, or I can end up in this other state. The nice thing about these abstractions with weights is that we can solve the problem of maximizing the SAST in this object by solving a mean payoff game. In this example, you can see that this mean payoff game, the solution to it would be circled by these blue circles. In the mean payoff game, and transitions are selected adversarially. So there is an environment that tries to minimize SAST and we want to maximize it. So if you see in this, from this state here, if I sample at the deadline at 2, my adversary can choose this transition, which leads me to in this state. And then I pick 1, the only option, and I can come back to 2 and stay in this cycle forever. So the value, the best value I can obtain here, SAST would be 1.5 using PETC. Now, if I choose 1 here, sampling earlier, I can go to this point where I can sample with 2 forever, having a value, a SAST of 2. So the mean payoff game gives me this strategy. Now, the question is how to find the correct way of finding an abstraction that whatever I get here makes sense in the concrete system. We choose an alternating simulation relation between the system, which tries to match transition weights. So in an alternating simulation, we want to find a relation between the state space of the abstraction and that of the concrete system, such that every point in the relation, say these two blue states here, satisfy the following. Every action that I choose in the abstraction, say 3, has a matching action in the concrete system, say 3 again, such that every transition in the concrete system has a matching transition in the abstraction, giving the end states being back in the relation. And moreover, the weights of the chosen transitions have to match. Now, observe that what I have here conceptually is an underpowered controller in the abstraction and an overpowered environment. So every action choice that I have here must exist in the concrete system. But I may have more options for the environment to play against me in the abstraction than in the concrete system, meaning that whatever specification I can satisfy in the abstraction should be carried on to the concrete system. There are some simplifications in our case, namely that the weight of a transition is actually the action that we choose. Remember the intersample time that we choose. So its average in the long run is what we want to maximize. So this simplifies things a lot if you do the algebra, and then it turns out that a normal simulation implies an alternating simulation on the right orders. So we have simulation-based methods to construct abstractions of ETC traffic from previous work, and we can use the same abstractions for the purposes of this presentation. Now, the interesting thing is how do the values that we can obtain in the abstraction relate to the values that we can obtain in the concrete system, particularly the strategy that we get by solving the mean payoff gain. So let's define a few values. The first is VADV, an adversarial value of a system given a strategy. Adversarial means that the environment wants to minimize SAST. So we showed an example before where PETC, the value in this case would be 1.5 because the adversary can keep me in this cycle forever. Now V of S is value of a system is the SAST given by the best maximizing strategy S star that can be applied to S playing against the environment. And this is also the example that we showed before. In the abstraction, this is obtained with the mean payoff gain. And in our case, V of SA of the abstraction is equal to 2, because that's where my strategy can ensure me that I can stay. Now, this also gives me, by definition, the adversarial value of the abstraction given the strategy from the mean payoff gain. What we don't know and is our holy grail is the value of the concrete system. We also define a cooperative value indexed by the state X, which is the SAST of the system starting at X when the transitions are selected, helping in the maximization of the metric SAST. So in this example, the SAST, the V co-op of this point is 3 because I can select this transition that gives me 3 forever. But for all other states, the best I can do is go to this point and pick 2 and have a value of 2. We define VU as the infimum amongst all states in the state space of this V co-op. So for this system, VU is equal to 2. Our main result is that if we have a proper abstraction, VU of the abstraction is an upper bound of the value of the best strategy possible on the concrete system. And the adversarial value from any strategy, I say, is smaller or equal than the adversarial value of the refinement of this abstraction on the concrete system, meaning we can have a better value with the same strategy refined. And of course, from any strategy, this is a lower bound to the value of the best strategy possible. So we have a way to get a lower bound and an upper bound. In practice, our approach would be to obtain a strategy after computing an abstraction, solving a mean payoff gain, then refine it to the concrete system and compute the adversarial value using these refinements. and estimate this optimality gap by computing VU on the abstraction. Let's see a numerical example to see how it works. We picked a two-dimensional linear system with a very aggressive triggering condition for the baseline PETC. And the top plot shows a comparison between the intersample times of the PETC in green and the associated strategy that we built using early triggers in the yellow dots. You can see that they start doing the same until this point when our strategy samples earlier than the deadline in red. Doing so allows that to avoid the situation that PTC gets into with those intermittent sampling bursts. Here we get a much sparser traffic pattern given a value of 0.6, more than twice the value of the PTC. Now VU, the upper bound, is 1.1, meaning that either our upper bound is too conservative or that our strategy is still far from optimality. So this ties to our conclusions. We show that sampling earlier than what PTC does can have massive improvements in the long-term average intersample time. So ETC is not optimal at all. And getting abstractions and solving min payoff games on them can be used as a way to attain such improvements. Now, as any approach with abstractions, it's computationally very challenging. So for future work, we are considering these questions: whether can we get tighter upper bounds than this VU, or is it really like the best we can do? Are there cases that we can classify where ETC is in fact optimal? And there is also an ongoing effort which is using a learning-based approach to find these optimal strategies. And we thought this would be easy for the learning-based approaches, but surprisingly, the strategies that we're getting with the min payoff games are very strong, very good, apparently, to the point that it's difficult to beat them with the learning-based methodology. But this is an ongoing effort, and we'll see where it goes. I hope you enjoyed this presentation, and I'm looking forward to your questions. Thank you.